Well, good morning, good afternoon, and good evening, everyone. Welcome back. So today, believe it or not, we are completing the proof that OCA implies all automorphisms of the Calkin algebra are inner. And we'll have time to talk about some generalizations and perhaps a little bit more as well. Let me just remind you before we continue that there will be no classes next week, but a week after that we continue, and that's our last week. So basically we have only 2 classes left. Oh yes, and one more thing that I owe to those who are taking course for credit. I haven't graded the homeworks yet. We'll do so by tomorrow. You'll get the results. All right, so let's go back to our proof. So here's the definition that you've seen before, but let's take a look at it once again. So this talks about subsets of the unit ball of B of H squared, right? So this is B of H, and this is our subset Z. Those subsets, such subset is narrow if all of its vertical sections are small, in the sense that each section is just consists of compact perturbations of a single operator, or rather, more precisely, it is included in the set of compact perturbations of a given operator. Epsilon narrow is slightly weaker, right? So we have this equivalence relation norm in the Calkin algebra of the difference is at most epsilon. And somewhat unfortunate terminology again, so it's a sigma narrow function. So now this time we have a function that maps B of H to B of H, right? So we have function, and here is its graph. We said it's sigma narrow if it can be covered by countably many narrow Borel sets. And then sigma epsilon narrow, you can guess what that means. And endomorphism has a sigma narrow lifting. Well, if it has a lifting which is sigma narrow, or rather if it's restriction to the unit ball, because that's all that matters, has a lifting which is sigma narrow. And a few more variants, but basically, I guess, if you know these, then you can reconstruct what the other ones are. And we need to prove 2 relatively small lemmas. But before that, we'll need a result from classical descriptive set theory. It is a theorem of Novikov. If X and Y are Polish spaces, and if you have an analytic subset of X cross Y, then if you look at the set of all of those sections X, such that, let's see, this is X, such that this set here, AX, right? I should probably remind you, AX is set of all Y, such that XY belongs to A. Right? So this is AX, right? The projection of these two Y is AX. So the set of all those indices, such that corresponding section is non-meager, is an analytic set. So this is result in classical descriptive set theory. Now, if you heard of one mathematician named Novikov, this is not him, this is his father. So this is Pyotr Sergeyevich Novikov, and the more famous one, Fields medalist, is Sergei Pyotrovich Novikov, right? So SP is different from PS, it's non-commutative. Actually, also the mother was quite established mathematician. But anyway, so let's go on to state our lemma. So suppose that phi is an endomorphism of the Calkin algebra, D is greater or equal than 1, E is element of part N, and there is a 1 over D narrow analytic set Z subset of dx tilde cross unit ball of B of H. Then for every A subset of X tilde, such that both A and X tilde minus A are infinite, at least one of the following applies. Possibility number 1, there is a C measurable 3 over D approximation of phi on dA. Or second, there is a B subset of X tilde minus A. Well, let me draw this second possibility. So here is X tilde. These are all subsets of natural numbers, so they're all sets of indices. Here is A. And what 2 says is that there is a B subset of the complement of A, and there are little a in the A, so little a is here. Let's draw it in a different color. Little a. This is not accurate picture, obviously, but I hope it's suggestive. There is a little b here, and both b and X tilde minus A union B are infinite. So this remainder of X is still infinite, and moreover, every uniformization Xi of Z there are, okay, something is wrong with the quantifiers here, sorry. Both B are infinite. Okay. For every, there is. Okay, this is better. So for every uniformization, there is C, which belongs to this complement, such that A plus B plus C belong to domain of Xi, and they satisfy Xi. Oh, sorry about this. Yeah, so right. Now it's better. So, and for every uniformization and every C such that A plus B plus C belongs to the domain of Xi, satisfy that Xi of A plus B plus C times QA is not equal modulo compacts up to 1 over D with phi star of A. Now, before I proceed to prove it, just what is the point here? Well, you see, if so, otherwise, if you look at the following map, A goes to Xi of A plus B plus C times QA is a lift of phi on D sub A. Right, the reason for that is that, remember, QA, maybe I should remind you, QA is phi star of P sub A, right? If this is true, then this would be always equal to phi star of A, and we would have a lift. But the point here is that we can choose this B and this A, so that any no uniformization of Z produces lift of phi star in the natural way. Right. So the meaning of this lemma is going to be clear in the following lemma, but let me just try to say what is going on. So we have this narrow set Z. Here it is. And now, basically, that set is as produced by the previous lemma that we just proved last time. And it is supposed to be giving us lifting of, well, not lifting, but epsilon approximation, where epsilon is roughly 1 over D of phi star. Now, remember, problem with the previous lemma was that it produced a countable family of 1 over the narrow sets that together cover the lift of our automorphism. And now we basically need to weed them out and get only one of them, and just get a single one, which is Borel, which works. And then we can put it into machinery that we studied before. Now, this lemma is a single step in that process. This lemma basically looks at this set Z and tests, is it going to produce such C-measurable approximation to our phi, right? So that's exactly what possibility 1 tells us, that we get the C-measurable approximation, and the option 2 tells us that that fails in a rather horrible way, in a way that we can basically record and just move on to the next one. Essentially, 2 puts a stake through the heart of the hope of Z ever being approximation on this set that remains. Now, each time we do that, you see, we give up these sets. So we are giving A and B, but still what remains is infinite. And you will remember that it didn't matter, in order to get an approximation on set D of E, okay, on the space D of E, it sufficed to get approximation on dy of E for no matter how thin, but just as long as it's infinite set Y, assuming that the lengths of these intervals En converge to infinity, which was the case. We just assured that that's the case. So basically, this lemma weeds out, basically tests one of these narrow analytic sets. All right. Now, in its proof, we define the following. So let me just do this. Okay, so here we have this set V, which is set of all triples A, B, C. A is in dA, B is in dx tilde minus A, C is in the unit ball of B of H. And they have the property that there is a C prime in the unit ball, such that A plus B C prime belongs to Z. And C and C prime are close. Now, close in what sense? Well, remember, Z, we need to multiply by this QA. Basically, what this tells us is that this C is what Z guesses should be phi star of A. Right. So basically, the definition of this set is C phi star of A. Just think of it that way. Is, or rather, is C up to 1 over D equal to phi star of A? Right. So that's what V asks. Now, Z is an analytic set. And what is V? Well, V is also analytic. V is a projection of Z, right? Because it's triples. So let me just write. So V is a projection of Z as analytic. What is important is that this relation here is Borel. Right? We proved this before, that this relation is Borel. Okay, so it's not projection of Z really. It is projection of, okay, so now since I started writing this, it's projection of the following set of all A, B, C, C prime, such that A plus B, C prime is in Z, and C is up to K, 1 over D equal to C prime QA. You see, QA doesn't change. It's a constant. So this is analytic set. So okay, so V is analytic as well. And now we look at this set here, this W of A. So it's all B in D sub X tilde minus A, so it's the complement, which have the property that the triple A, B, and phi star of A belong to V. Right, so W of A is set of all B's such that if you plug B as the second coordinate in V, then V somehow clicks. It actually belts out the correct answer. What exactly is the approximation? And we define this for every A in D sub A. Okay, so now we just ask a question. So so case one, for every A in D sub A, W of A is relatively comeager in D sub X tilde minus A. Okay, now what do we have then? Well, then just fix Xi, which is uniformization. Actually, not Xi. Do I want to call it Xi? Theta. Let's call it theta. Xi is going to be something else. Uniformization of Z. Okay, and now let's just see. Let's draw a picture here. So we have W of A. Sorry about this. I was sure that I knew this proof, so I was thinking about other things. Just a second. Oh, okay, you're right. Right. So I don't want this uniformization. Now I'll look at the following set. The set of all AC in dA cross B of H less or equal than 1, such that the set of all B in X tilde minus A, such that A, B, C belongs to V, is relatively comeager in D sub X minus A. Let's call that set, okay, I used Z, let's call it Y. By Novikov, this is Y is analytic. Okay, so we can by Janko von Neumann, we can choose C measurable uniformization of Y. So let theta be C measurable uniformization of Y. This is V. And now we have our assumption that W of A is relatively comeager in D of X tilde A. Now, what that means, since intersection of two comeager sets is non-empty, so then for every A in the domain of Y, there exists B, which belongs to this comeager set W of A, and moreover, it is such that, let me use some visible color here. So here is our B. And it also has the property that A comma B comma theta of A belongs, like right now. So and A, B, theta of A belongs to V. All right, but now what does this mean? We have then there is C prime such that A plus B comma C prime belongs to Z. And moreover, if you look at theta of A, theta of A is equal to modulo compacts up to 1 over D to C prime QX tilde. And there is also C double prime such that A plus B C double prime belongs to Z, and phi star of A is equal modulo compacts up to 1 over D to C double prime QX tilde. Now, if you just add up these epsilons, so we have 1 over D here, 1 over D there, and what we get is that theta of A and phi star of A are close, right? This set was too narrow, so so we have that A goes to theta of A is 3 over D approximation, and it's immeasurable. Right, but we had this assumption here. We had assumption that this set WA is comeager for every A. Now, what if that doesn't happen? We have case 2. There exists A in dA such that W of A is not comeager. Okay, now what does it mean not to be comeager? Well, it means that there is some basic open set such that WA is relatively meager on that set. Right. So there is a basic open set, let's call it U, such that WA intersected with U is relatively meager in U. But now what is, remember that both W of A and U, they are subsets of this set D sub X minus A. So this is a product space, like Cantor's set type product space. And we pretty much know everything about meager sets in such spaces. So by the theorem that we proved before, we can find this infinite sequence of disjoint intervals. And inside each one of those intervals, we can find some element in this, which is indexed by those intervals, so that okay, let me write it down. right? So there are Jn, which are finite subsets of d of x minus a, disjoint. And there is, let's just see what notation I use. There is S of n, which belongs to d sub j of n. Actually, sorry, this wasn't. This is subset of x minus a, so this is the index set. And there is S, so that if you look at set of all y in d sub x minus a, such that there are infinitely many n, such that y restricted to Jn is equal to Sn, then this set is comeager. And if we intersect it with U to start with, right, so it's relatively meager in U, then this is intersected with W of A is empty. Okay, so let me draw a picture at this point. Now, U, also, we can assume that U itself is of that form, that U is of the form J sub T for some J, which is finite subset, J, which is a finite subset of x minus a, right? It's a basic open set. This is what basic open sets look like. Okay, so we have this J that U corresponds to, and we have J0, J1, J2, and so on. So we have this infinite sequence of intervals. Now, what do? Well, we just discard infinitely many of them and take, let's say, just the even ones, and take B to be the union of J2 n's, and a little b naturally to be the sum of those S of 2 n's, right? So little b belongs to this product space. Now, if you look at what happens, well, this exactly means that B and this set satisfy, let me roll back to it, that satisfy this, that no matter how you choose uniformization, and no matter how you choose C in this remaining part, this A plus B plus C, if they belong to domain of C, they're not going to be equal to up to 1 over d to phi star of A, because Z is avoiding this set, the set of good candidates for phi star of A. Right, so that is the proof of this lemma. Any questions? So I made it slightly messier than necessary, but basically the idea is, I hope, clear. Right, so there is this little ingredient of descriptive set theory, which is quite important here. Now, the next lemma is a consequence of what we just saw. Suppose phi is endomorphism called in algebra, this is greater or equal to 1, E is in part n, and phi has a sigma narrow 1 over the approximation on some dx tilde of E. So x tilde is some infinite set here. Then the following holds. There is an infinite A subset right. There is an infinite A subset of x tilde and the C measurable 3 over d approximation to phi on dA of E. Right. So there is a single set on which we have a single approximation. We lose a little, right? So it's we trade 1 over d to 3 over d, but it doesn't matter because we have arbitrarily good approximations anyway. And the second part says that there is a C measurable 3 of the approximation on d of f for all f in part of n. Right. So okay. So let's prove part 1 first. This is pretty much a consequence of the other lemma. Okay, so we assume otherwise. And now we fix those 1 over the narrow analytic sets Zn that cover the graph of 1 over the approximation of phi on this set. And okay, so we have countably many sets and we'll do recursion in countably many steps, basically killing off one of the approximations in each of the steps. And now we fix a C measurable uniformization Cn of Zn. Right, so at this point, what we have is this sequence of C measurable functions. Each one of them uniformizes one of these. And now our assumption is that one fails. So this is proof of one. I didn't say that. So assumption is that no matter how we choose an infinite set of indices, then there is no C measurable approximation to phi on the A of E. Now of course, Cn is probably not approximation, but let me just say here. So for every A subset of X, if you look at the following, look at map from dA to B of H less or equal than 1, that sends little a to Cn of A times QA. So this is not approximation. 3/3 approximation, right? So for every n, I think this is our assumption. Okay, and now the plan is to find the partition of our set X into disjoint infinite sets, An and Bn. So these are all infinite sets. And to find A of n in each D of An and B of n in D of Bn, so that if we add up all of these, then you know, these guys witness that we have contradiction. Namely, if we add up A's, An's and Bn's, then if you choose any m and look at Cm of A plus B, this is not equal modulo compacts to phi star of A plus B. Now, to prove this, what we need is exactly that previous lemma. So let me just roll back to the lemma. The lemma, as I said, lemma is going to make more sense now when you see what was its purpose. So let me, here it is. Right. So we'll be applying lemma at each step. So Z will be one of those Zns, and A is set that remained so far. Sorry. So at any given point, we have this. We choose an infinite subset of what remained. And we say, okay, so is there a measurable theory approximation on it? Well, our assumption was that there isn't, so there isn't. Now, what part 2 tells us is that we can find an infinite subset of the complement so that the complement is still infinite, so we have still more to work for, in the recursive construction, and we can find an element B of dB so that no matter what uniformization we take, in particular the uniformization that we took at the beginning, there is going to be something that witnesses that C is not a lifting. Right. Right. So this is exactly what we need in the recursive construction. And where am I? Oops, I went too far. Right. And this is it. So this concludes the proof. Okay, that was somewhat underwhelming, I guess. Okay, any questions? All right. Okay, so let's just recap the whole thing and see how this all works out. So, okay, finally, this completes the proof. So let me just basically review the entire proof step by step. I have a reason for doing that. So basically, we didn't prove parts of the proof. We didn't give parts in this order that actually appear in the proof, because I just thought that it would be more instructive to do it in the reverse order. Almost reverse order, but here is the proof in the proper order. So first, in the first step, and I'll just indicate OCA is used in the first step, we prove that after we fix an automorphism, that for every E in part, phi has a C measurable epsilon approximation on D of E for all epsilon greater than 0. Okay, actually, I skipped a few steps here. So it was longer than that. Right. Okay, so this is what comes after what we just did, right? So what we had first was getting this sigma narrow epsilon approximation, and then working through this to get a single approximation on some set. And then after that, we did some descriptive set theory and some trickery with stabilizers to get a continuous lifting on some infinite set. And then after that, more stabilizers, and got the product type lifting on some D of E. And that brought us to this realm of approximate star homomorphisms. And then we use this Ulam stability result that every approximate star homomorphism can be approximated by a genuine star homomorphism. And from there, we got that on every E, phi has a lifting, which is conjugation by some partial isometry. And then we corrected that to get a unitary by conjugating with the opposite one, just to kill off the Fredholm index. And finally, in the last step, used OCAT once again to prove that this coherent family of unitaries, which implements this, can be uniformized by a single unitary. And therefore, our automorphism is composition of two inner automorphisms, and therefore inner itself. Now, going through this proof made me think that actually it can be simplified considerably. In particular, the part of the proof that we went over today may be unnecessary. So if anybody is interested in discussing this further, it seems to me that the proof can be considerably simplified and shortened by essentially doing things in a different order. As I said before, the original grandfather of all proofs of this sort is Saharon-Shellak's proof that all automorphisms of essentially L infinity mod C0 are trivial, in the sense that they're given by almost permutation of natural numbers. Or you could say that every automorphism can be lifted by an endomorphism of L infinity. And all of these proofs basically follow steps in Saharon's proof. It turns out that some of those steps are just not necessary in the Calkin algebra. So as I said before, there is entire part of the proof which uses Martin's axiom typically, which is just not present here because we have the isometry trick. And now I realize that there are actually more tricks that could be used in the Calkin algebra. One of them has to do with that issue of sigma narrow, but automorphism which is sigma narrow, but maybe not narrow. But anyway, so let me stop. I mean, if anybody wants to talk more about this, I'll be glad to say a few more words about that. But let's go on to some related results. So, I mentioned before that Sam Koski and I had a conjecture some years ago that if you have corona of separable non-unital cyst algebra, then under continuum hypothesis, you can construct whatever you can construct. That there are 2 to the F1 automorphisms, and under some forcing axioms, such as OCA, all automorphisms should be trivial in some sense. Well, that conjecture has almost been verified by Paul McKenney and Alessandro Vignati. And here is the final theorem. Well, final for now, that OCA and MA. MA is Martin's axiom that we didn't discuss, that we didn't need, but it seems to be needed in this context. They together imply that every isomorphism between coronas of separable cyst algebras has a Borel measurable lifting. Now, this part with Borel measurable lifting, we would like to have something more precise there. Something that resembles a CPC lift or something like that. It's not clear what the right definition is, but this theorem actually already has many interesting consequences to rigidity of coronas, assuming these axioms. Okay, so what needs to be done in order to improve these theorems is 2 things. So I already mentioned one. We don't know what is right definition of trivial yet. Having Borel measurable lifting, well, it's as good as we could do. Just a word about set theory. You see, what happens here is that we run into independence phenomena, that whether there exists an automorphism which is outer or not may depend on the axioms of set theory. And also whether 2 coronas are isomorphic may depend on the axioms of set theory. Now, if you say that there is an isomorphism which has a Borel measurable lifting, that is very unlikely to be independent from set theory, because this is what set theorists call pi-1,2 statement. No, it's not pi-1,2. It is, okay, once you're given Borel measurable lifting, so it's sigma 1,3. But once you're given Borel measurable lifting, to check that indeed it is a lifting of an isomorphism, you just need to check that for all A and B, that it behaves like an isomorphism, and that it's onto that. That's why I need pi-1,2. And okay, what pi-1,2 means is that you have 2 quantifiers over the real numbers. And when I say real numbers, I mean any Polish space, including unit ball in strict topology of some separable, of multiplier algebra of separable cyst algebra. That's a Polish space. And pi-1,2 just means that you have quantification of form for all blah blah, and then exists blah blah, and then there are no more quantifications or Polish spaces. Well, statements of this form are absolute between reasonable models of set theory, which means that assuming OCA or MA or continual hypothesis, or basically any reasonable set theoretic assumption is not going to change their truth. So that they are somehow robust for the tricks that set theorists can use at present. So in that sense, this theorem is quite satisfactory, is that it gives us that under these assumptions of OCA and MA, only those isomorphisms which have to exist. Right. Now, to improve this, we would need a better Ulam stability result. The best Ulam stability result is due to the same two people, McKenney and Vignati. It is slightly stronger than what I presented. What they proved is that you have Ulam stability for approximate homomorphisms from any finite dimensional cyst algebra into an arbitrary cyst algebra. So for every epsilon, there exists a delta, so that if you have a delta epsilon homomorphism from any finite dimensional cyst algebra into any cyst algebra, you can epsilon approximate it by a genuine star homomorphism. Right. Now, this is related to something called Caddison-Kessler stability. If you know what that is, you probably see the connection. If not, never mind. This is not the moment to talk about it. All right. Now, in the abelian case, we have a perfectly satisfactory result. So that was done by Alessandro Vignati using results of Shamrel for this part here. Basically, in the abelian case, there is a strong Ulam stability result. And here is the theorem on the same assumptions, OCA and MA. If you have locally compact, non-compact Polish spaces X and Y, or in other words, if you have non-unital abelian separable cyst algebras, right? So that's exactly C0 of X and C0 of Y are arbitrary abelian non-unital separable cyst algebras. And if you look at their coronas, right, continuous bounded functions modulo C0 functions. So if you have isomorphism between such coronas, then there is the most concrete possible reason for the existence of such an isomorphism. If this is your X and this is your Y, then you can remove a compact subset from X. So you have a co-compact subset X0, and in Y you have also co-compact subset of Y0 of Y, and there is a homeomorphism F between those sets, such that this map composition with F lifts your isomorphism. So this is really beautiful and very satisfactory result. Let me just say, under continuum hypothesis, this fails miserably. So under continuum hypothesis, for example, so let me just give you one example. So if X, Y, actually, let me just say X. I don't need Y. So if X is countable, locally compact, then this CB of X modulo C0 of X is isomorphic to L infinity mod C0. And of course, this is just a CB of natural numbers modulo C0 of the natural numbers. There are actually Aleph1 non-isomorphic cyst algebras of this sort, but they're all isomorphic here. This is really essentially a classical result of Parovichenko. Right, so all this pathology disappears if you assume forcing axioms. Right. So that's the abelian case. And there are other cases in which positive results can be proven. I'll just mention one. So here O infinity is Kuntz algebra O infinity. It is universal cyst algebra generated by isometries Sn, which have the property that, okay, so it's isometry Sn star Sn is equal to 1. And on the other hand, if you look at Sn star, these are orthogonal projections. So this is 0 if n is different from m. I'll say, basically, Alessandro's result imply this for all other Kuntz algebras, but this one is more interesting. So if you assume OCAT Okay, you need MA here. The Calkin algebra is not isomorphic to corona of stabilization of O infinity. Now, this follows from the fact about Borel lifting. You see, if you have a Borel lifting of something like this, so it's a Borel map from unit ball of B of H into unit ball of the multiplier algebra of O infinity tensor K in strict topology, that's never going to lift an isomorphism. That's pretty much an exercise. Why this matters? Well, here's the reason. You see this algebra on the right-hand side, it has a K-theory reversing automorphism. You see K1 of this algebra is Z, and K0 is just trivial, which is exactly the same as for the Calkin algebra, which is the question, are they isomorphic non-trivial? So there is no K-theoretic obstruction, and yet they're not isomorphic, which is not so surprising for non-separable algebras, but still there is a reason for looking at this case here. You see, this algebra has K-theory reversing automorphism. So if Calkin algebra and that algebra were isomorphic, then that isomorphism would transfer to K-theory reversing automorphism of the Calkin algebra, which is the most interesting question here. Can you construct something like that? So question is, are these two coronas isomorphic, say, assuming continuum hypothesis? I don't know. And well, nobody knows. Also, what we don't know is we don't really have a non-trivial example of simple coronas for which the question, are they independent, the question, are they isomorphic, is independent from ZFC. So, and here is the questions, right? So are there examples of simple separable C algebras A and B such that this assertion that their coronas are isomorphic is independent from ZFC? No idea. The best result in this direction is due to Said Ghassemi. So if you look at algebras of the following form, look at some X subset of natural numbers infinite, and look at the direct sum of Mn Cs, right? So there are many non-isomorphic algebras of this sort. What Said proved is that there are many pairs of algebras of this form. So if A and B are of this form, for which the question, are their coronas isomorphic or not, is independent from ZFC. Right. But they are not simple, but still they are generally non-commutative. They are not just modifications of some commutative algebras. Next topic is endomorphism. So here is a conjecture that I made a long time ago. Actually, when I made the conjecture, I didn't even know what a C-star algebra was. It wasn't stated in terms of C-star algebras. It was stated in terms of Boolean algebras, but it's equivalent to this. That PFA, now PFA is a strengthening of OCAT plus MA. I was just using the strongest axiom that I could get hold of. PFA implies that every endomorphism of L infinity mod C0 lifts to an endomorphism, which is not necessarily weak star continuous of L infinity. Right, so you have endomorphism from L infinity mod C0 to itself. Right. If it is automorphism, then Shelah and others proved that it does lift to an endomorphism. But what if it's not an automorphism? If these are quotient maps, so here is phi, does it lift? Now, this not necessarily weak star continuous part, it is an exercise, basically assume that there is an, well, I'll just choose an alpha filter, non-principal alpha filter of natural numbers, and it can be easily used to construct non-weak star continuous endomorphisms. I proved a weaker form of this conjecture and got carried away. Here is what happened. So Alan Dow proved in 2014 that conjecture is false. So in ZFC, there is an endomorphism of L infinity mod C0 that does not lead to an endomorphism of L infinity. Right. So you see, this basically goes back to that story of trivial. What is the right definition of trivial automorphism? What is the right definition of trivial endomorphism? Well, essentially, what Alan proved here is that for endomorphisms of L infinity, there probably isn't the right definition of trivial because these ones are seriously non-trivial. Now, okay, this is more general topology than C algebras, but there is a reason for talking about that. You see, one of the points that I'm trying to make here is that L infinity mod C0 and the Calkin algebra look very similar, but they're actually very different. In many ways, they are quite different. And let's see the analogous question for the Calkin algebra. So if you look at endomorphisms of the Calkin algebra, what is the right definition of trivial? Well, first, if you look at Mn of the Calkin algebra, it is isomorphic to the Calkin algebra. Right? Because Mn of B of H is isomorphic to B of H, and the compacts go to, I mean, there is unique ideal in both cases. So we can fix an isomorphism between Calkin algebra and this amplification of the Calkin algebra for every n. And now that gives us trivial endomorphisms, right? Basically, if you look at tensoring with the 1 sub n and composing this isomorphism, you could say that is a trivial endomorphism. And what Andrea Vaccaro proved is that under OCA, these are the only endomorphisms. Right, so more precisely, if you assume OCAT, then every endomorphism of Calkin algebra is unitarily equivalent to this. So what your endomorphism is doing, so you first amplify by 1 sub n, and then compose by this isomorphism, and then perhaps compose with the inner automorphism, and you get all endomorphisms that way. There aren't any others. Right, so they're as easily described as possible. And in particular, that they are classified by this index, right, by this n. And uniquely determines up to unitary equivalence what your endomorphism is. And if you compose those endomorphisms, then those indices multiply. So what that means is that if you look at endomorphism group of the Calkin algebra modular composition, with respect to composition modular unitary equivalence, it is just isomorphic to positive natural numbers with respect to multiplication. Now, in the proof that I presented at several places, if you go back, you'll see that actually you don't need to assume that you have automorphism. You just need an endomorphism. The proof works. But there are some places where it is non-trivial. So basically, Andrea worked this out. And for example, that last part, uniformization of coherent families of unitaries. Well, you don't have unitaries here, so you just have to figure out what to do there. But anyway, so all endomorphisms of the Calkin algebra are trivial in this model. All right. Now, here is a beautiful corollary, which is actually a part of the homework, for fourth homework. If you assume, oops. So if you assume OCA, and now look at all C-star algebras A, such that A embeds into the Calkin algebra. What can you say about those? Right, so if A embeds and B embeds, and you somehow use A and B to produce a third algebra, when can you know that third algebra embeds as well? Well, under OCA, you don't really know much. So here is a striking consequence. There are C-star algebras A and B, such that A embeds into Calculin algebra, B embeds into Calculin algebra. But if you take tensor product of A and B, and no matter what tensor product you take, actually one of them you can choose to be nuclear, so it's just minimal tensor product. This tensor product does not embed into Calculin algebra, right? Which is somewhat counterintuitive. Right? Remember, I mentioned before this Say's result that is, well, related, that if you take a Calculin algebra tensor product with itself, that it is not isomorphic to the Calculin algebra. Right. So that definitely that follows from this, but you know, this result is in the FC, and this one is proved using OCA. And the second consequence is that there is a countable inductive system AN, such that each of the components of the system embeds into Calculin algebra, but the limit doesn't. So the algebras are necessarily non-separable, but the system is countable. So this is an exercise for homework, so I'm not going to tell you, but just basically think essentially at a big hint is this theorem here. All right. Now, of course, when you see something like this, you may wonder, well, do you really need additional axioms? Well, both for Vaccaro and for this. Note that result for L infinity is mod C0 and for Calculin algebra, that they're completely incomparable to one another. These results about endomorphisms. And actually it was proved before Andreas' results, because proof is easier, I guess, by Ilan Hirschberg, Vignati, Alessandro, and myself, that if you assume continuum hypothesis, then indeed the opposite thing happens. Implies the negation of the conclusions of the corollary and theorem. Essentially, you have many endomorphisms of the Calculin algebra, which are very different from any of these. And well, you can see from the title that actually we're going for something else. Basically, the main theorem is in ZFC that if you have any C-star algebra of density character Aleph1, it embeds into the Calculin algebra. Now, this resembles properties of saturated C-star algebras that are universal for algebras that have the same theory or same existential theory at least. But the proof is necessarily different because Calculin algebra is not countably saturated. And as we saw before, you can embed separable C-star algebra into Calculin algebra and embed it into some other separable C-star algebras so that you cannot extend the embedding. So this needed to be done in a more complicated way. But you see, one of the consequences of this result is that if you look at all C-star algebras A, such that A embeds into Calculin algebra, this is exactly set of all A, such the density character of A is at most Aleph1. So this is under CH. Right, because we proved that all of them embed, and vice versa under CH, density character of Calculin algebra is Aleph1, so you cannot embed anything bigger than that. All right, so right, okay, so that basically finishes this part of the story. And any questions before I go on to the next topic? Okay, so what I want to say is something about applications, essentially, of all these two classifications. So this is one of the standard ways that massive C-star algebras are applied to classification. Let me just introduce some definitions. If you have two star homomorphisms from C-star algebra A into C-star algebra B, then we have these equivalence relations on those. First one is unitary equivalence. Well, they are entirely equivalent if and only if there is an inner automorphism of B such that when you compose with it, you get the other one, right? So here is the picture. So here is phi, here is psi, and here you have, let's see, it goes in this direction. Here you have conjugation by unitary. You can complete the triangle so that this commutes. And a weaker notion, approximate unitarily equivalent. So in this case, you again have phi and you have psi, but now you have sequence or rather net of unitaries, such that if you compose by conjugations by those unitaries, then point-wise in point norm topology, you have convergence. All right. Now, here is an exercise. If B is countably saturated or even countably quantifier free saturated, and A is separable, and if you have two star homomorphisms from A into B, then these two relations coincide. Right? Obviously, one is stronger than two, and to prove that two implies one, you just need to write down the right type and check that it is quantifier free type and that this works. Again, for calculus algebra, this doesn't work. The statement is just false. Okay, so this is a reason why saturated cyst algebras are useful to have in the range here. Right, and as I said, degree 1 saturation doesn't suffice, and you even have this example that we discussed before with the Carl algebra and the calculus algebra. Okay, so let's look at asymptotic sequence algebra. B infinity, remember, is L infinity of B modulo C0 of B. And this is with alpha powers the most popular kind of massive cyst algebra. Now, these algebras have very large and automorphism groups and endomorphism semigroups. So here is one example, important kind of endomorphism. If you have an injection from natural numbers to natural numbers, then you can define a map F star from B infinity to B infinity by its action on the represented sequences. So really, I mean, the way that I wrote it here, F star really maps L infinity of B to L infinity of B. Right? I'm just reindexing the sequence, but the fact is that it preserves C0, so it naturally defines endomorphism of B infinity. And also note, remember that we think of B as sitting inside this. So there is a diagonal copy of B inside this algebra, and we identified with that. Well, F star restricted to B is just the identity on B because these are constant sequences, so nothing is happening. And actually B is exactly the fixed point algebra for this group of endomorphisms. All right, so now here is an exercise. If U is an ultrafilter, and if you have an injection from natural numbers to natural numbers, and you define F star in the same way, well, you may not, I mean, this may not define an endomorphism of the alpha power. It actually defines endomorphism only in the trivial case if F is equal to the identity modulo the ultrafilter. In other words, for alpha powers, the only endomorphism of this sort is the identity. There are no others. You know, this exercise, it's really, when you see what is going on, it really boils down to a little combinatorial lemma about functions. And it's not even about ultrafilters. So basically, lemma just says that if you have a function like this, then you can partition natural numbers into finitely many pieces, I think 9 pieces or something like that, so that one of those pieces is the set of fixed points, and any other piece is mapped elsewhere. So if you look at f of the first piece, it goes to union of the other pieces, and same for each other piece. And then if you look at this, it just implies that as a map on the alpha power, it just doesn't, it makes sense only if f is constant. Sorry, not constant, identity, if f is the identity map. Which basically means that what I'm going to say next just doesn't work for ultrafilters, algebra powers. And here is that. So this is a theorem that in some form appears in a paper of Kirchberg and Phillips, and in a more recent paper by Jamie Gabe, it appears in slightly different form. Suppose that A is separable, and we have a star homomorphism from A into B infinity, then the following two are equivalent. Phi is unitarily equivalent to some star homomorphism from C from A into B, right? So here B is diagonal copy of B. And 2 says that for every injection from natural numbers to natural numbers, if we compose phi with f star, what we get is unitarily equivalent to phi. So as I said, this is quite useful in classification, and this is one reason why often asymptotic sequence algebra is more useful than alpha power in some situations. You know, it's a trade-off, because with alpha powers we have Walsh's theorem, so we know that alpha power is very much similar to what we had downstairs. It's just elementary extension of our algebra. B infinity is not, you know, you can compute theory of B infinity, but it's rather messy. But you have this. So this is what I wanted to sketch proof of right now. Okay. Okay, so proof. So first note that so for phi and psi, which map A into B infinity, that phi is unitarily equivalent to psi if and only if phi is approximately unitarily equivalent to psi. I'm not sure if I if I mentioned notation, but basically this is the reason, because B infinity is countably saturated and A separate. Okay, so let's prove first 1 implies 2. Right. So what does this say? So assume 1. Find fix unitary in B infinity, such that if I compose phi with A du and call it C, it satisfies that the image of A is subset of B. All right. So what this implies is that then for every f n to n injection, if I look at f star and compose it with C, I get C back. Right, this is the property that we want. Okay, so now fix F. I need to prove this part too, that F star composed with phi is unitarily equivalent to phi. So then F star composed with phi, what is it? Well, it is F star composed with, okay, so since C is ADU composed with phi, then phi is ADU star composed with psi. All right, now what is this here? Well, I'm composing first with inner automorphism and then with psi. So what will this be? When you work it out, it is really conjugation by F star of U star, and then composed with F star composed with psi. But we just checked that is just psi. So F star disappears, and now this is this, and psi is just ADU composed with phi. So I have two inner automorphisms and phi. When I compose them, I just get a single inner automorphism. So it's AD F star of U star U composed with phi. Right? So F was arbitrary, and we just checked that F star composed with phi is unitarily equivalent to phi. Okay, so this is actually less interesting implication. So let's prove 2 implies 1, which is the interesting one. So assume 2. Right, and now let's fix some sort of a lift for phi, right? This is what we were doing before using axiom of choice, but we'll need a lift of a specific form. Lift of phi. So okay, so what is lift? So it's a function that sends a to L infinity of b. But what is L infinity of b? Well, it's really product of countable many copies of b. So what I mean by it is that okay, I used to call this phi star, but phi star of some a will be of specific form. So really, I just want to write down what are the coordinates of a. So it's of the form phi n of a for n natural numbers, and phi n maps a to b for each n. Now, phi n's are not star homomorphisms, they're not CPC, they're not linear, they're nothing. They're just picked using axiom of choice. Right, so basically phi n is really composition of phi star with the appropriate projection map. Now we are assuming that composition of phi with any of those F star maps is unitarily equivalent to phi itself. So here is the claim. For every finite subset of A, for every epsilon greater than 0, there exists some m in n such that for all n greater or equal than m, let me just make sure that I go in the right direction. Okay. There exists a unitary V in B such that the following holds: phi n of little a is V phi n of little a V star for every a in F. right? So from some point on, these maps look similar. They are approximately unitarily equivalent, at least on these finite sets, right? So note that M depends on both F and epsilon. Okay, so proof, of course, assume otherwise. Okay, so fix the witnesses for this. So fix F epsilon for which this fails. And now for every M, there exists an N of M. Actually, I'm not going to call it N of M. I'll call it F of M, which is greater than M. And I'll also make sure that it's greater than F of I for all I less than M, right? So we are defining this recursively less than M, such that there is no V unitary in
Sorry,
B.
can I ask a question?
Yes, of course.
What is the role of epsilon in the claim?
Oh. Thank you. Thank you for asking the question. It's a big role, of course. Yeah, right. So of course it's this, right? So everything happens up to epsilon. Thank you so much. I would be in a big trouble if you didn't ask this question. Right, so now it's clear, right? Yeah, thank you. Right. Okay, such that there is no V. I guess I would have noticed it now, but it's better if you notice. So there is no V such that Vn of A minus Vm of A, Vm is less than epsilon for all A and F. Right, so this is a finitary statement, and you see, I just produced this function F. Right, so then F sends natural numbers to natural numbers, and it's injectional because I made sure that it's cyclically increasing. Okay. Now, bare assumption, F star composed with phi is unitarily equivalent to phi. Right, so it's by 2 that we assumed. But then, okay, so fix U. Now you see what is U? U is unitary in B infinity. But what does that mean? What do unitaries in B infinity look like? Well, they're really sequences of unitaries. This is, for model theorists, this is the fact that unitaries are definable. To cyst algebras, they would say that they're defined by weakly stable relations. Basically, if you look at defining formulas for being a unitary, if something almost satisfies it, you can use polar decomposition to actually get unitary which is close to it, which satisfies it. So then U is really, really belongs to the unitary group of B to the nth. I mean, it's infinite sequence of unitaries in B. But now, what do we have? Is that for every A in A, if you look at, let's see, so F star, right, that phi of A is equal to ADU composed with F star of phi of A. Okay, but what does that mean? That means, therefore, for every A in A, if I look at A minus Now U, okay, here I can think of U as sequence UN. If I look at if I look at phi of A, the nth coordinate of this, which is I actually introduced notation for that, right? So I had my liftings. So it is phi m of A minus, and here I have um composed, this is not what I wanted. I wanted f of m here. Let's see, what side do I want this? So conjugate. Right. I think it's phi m minus right? And here I have phi f of m of A star, right? In norm, this converges to 0. But this is exactly what I said doesn't happen, right? Right. So this is how I chose them. For the elements of this finite set, let's see if I chose them that way, or did I choose them? Okay, it seems that I chose them the wrong way. Okay, okay, so I have to multiply by. I always forget what side to multiply on, but if I put it this way, it is the same, right? So this converges to 0. So it's eventually less than epsilon, and that's exactly for A in my F. This is exactly the contradiction. Okay, so we have this claim. So for every finite set, for every epsilon, there exists an M. So that from that point on, there is a unitary which does this. And now from here, you just assemble the map. Okay, so we are assuming 2, and we want to prove, we want to construct embedding, star homomorphism from A into B. So what do we do? So we write A as an increasing union of fn's, so that each fn is finite, and find epsilon n. I think something like epsilon n is 2 to minus n should do. And what do we have now? So fix these. And what do we know? So let's just go back for a moment to see. Actually, I can copy this right here. Okay, so here's what we have. It's not claim anymore, but for every f, now for each one of these fn's, and for every epsilon n, right, there exists this m, which is mn up. N was a bad choice. Okay, so that for every k greater or equal than m, there exists this v, such that phi k of A times v phi m A v star is less than epsilon m for every A in F n. Mn, this is Mn. Okay. So now what do we do? So there is V this V actually also, let's see, so I can just call this Vn. And, oh, sorry, I'm going to overtime. So am I saved by the bell? So basically, the point is that if you look at it's something like product I less than m of VIs, this conjugation ADUM converges, composed with phi, converges to the embedding as required. Maybe I should stop here because I'm actually, frankly, not sure exactly how it was, but it's something like this. So, all right. So anyway, there are no classes next week, so we continue on Monday in 10 days from today. And right, so well, stay safe, and I'll see you then. So this is in Jamie's paper. I'm not going to put up a reference. Actually, I'll just write down what the end of the proof is on the slides, so that you can look it up if you're impatient. And see you on Monday in 10 days.